solved up to problem number 8, correct? Model 3, problem number 8. That is problems on analysis of PSC beams. Okay. Now we'll solve a few more problems. This 9th problem, you can take this as homework. Okay. You solve by yourself, and in the notes I have provided the answers. You just cross check with the answers. Still, if you are not able to solve it, you can contact me anytime. Okay. Now we'll solve one more problem. That is problem number 10. All of you write this problem. So I'll write the diagram. This is problem on the box girder, okay, or bridge girder. Just go through it. A post-tensioned bridge girder with unbonded tendons is of box section of overall dimensions 1200 mm wide and 1800 mm deep. Okay, overall dimensions are given. Yes, any? Yes. Overall dimensions are 1200 mm wide and 1800 mm deep. Okay, with wall thickness of 150 mm. Let me write the diagram for the same. He says that it is of a box section. Okay, box section. Okay, with 1200 mm wide and 1800 mm deep, with thickness of wall as 150 mm. Okay, let us write a box section now. And write the corresponding dimensions as well. V is equal to 200 mm and overall depth is given as 1800 mm. 1800 mm. Okay, with wall thickness of how much? 150. 150. Okay. The high tensile steel has an area of 4000 mm square and is located at an effective depth of 1600 mm. Okay. The area of pre-stressing steel is given. Correct. Area of pre-stressing steel is given. Let me write the area of pre-stressing steel here. Okay. And it is located at an effective depth. D is equal to how much it is given? 1600 mm. 1600 mm effective depth. Okay. Then the effective pre-stress in steel after all losses is 1000 Newton per mm square. Effective span of the girder is given as 24 meter. FCK is given. FP is given. Correct. Characteristic strength of tendons is given. It is asked to find the ultimate flexural strength of the section. Okay. Therefore, here the given data is B is equal to 1200 mm. Overall depth is given as 1800 mm. Then wall thickness is 150 mm. Then area of pre-stressing steel is given as how much? 4000 mm square. 4000 mm square. Then effective depth is given as 1600 mm. Then effective pre-stress after all losses. Effective pre-stress after all losses is given as 1000 Newton per mm square. 1000 Newton per mm square. Then length of the beam is given as 24 meter. In terms of mm, it is 24,000 mm. Then FCK is given, FP is given. FCK is equal to how much? 40 Newton per mm square. 40 Newton per mm square. And FP is equal to 1600 Newton per mm square. Okay. Then coming to the, so it is this box girder, no, it is analyzed as an I section only. Whatever the procedure we follow for I section, no, same procedure we have to follow for this box girder. Okay. So here, if you assume this box girder as I section, you will get two webs. Okay, two webs. Therefore, the total width of web will be 150 plus 150. Okay, 150 plus 150, it will be 300 mm. Okay, so width of web is equal to 2 into, there are two walls, wall thickness, 2 into wall thickness, which is equal to 2 into wall thickness is 150 mm. You will get BW as 300 mm. Okay, then depth of flange, how much it is? 150 mm. Okay, it is analyzed similar to the I section or double T section. Okay, 150 mm. 150 mm. Okay, nothing but depth of flange. Okay, so this is all given data. Now we have to assume case 1 or case 2. So in case of box girder, 95% neutral axis lies in the web portion only. So better you assume second case, that is depth of neutral axis lies in the web. Then you can have a cross check. Then we can proceed with finding the moment of resistance. Okay. Now write a note assuming that the depth of neutral axis lies within web. Okay. If you assume that the depth of neutral axis lies within the web, then what is the procedure we have to use? Let me go to the theory part. This is the procedure we have to use. First, we have to find APF, then APW. Okay. Then we have to find XU by D. Then you need to check whether the depth of neutral axis lies in the web or not. Okay. First, we will find APF and APW. Total AP, total area of resistance steel is given. Okay. So we know that. APF is equal to, what is the formula? So here we have the formula 0.45 FCK into BF minus BW to DF by FP. 0.45 FCK into width of flange minus width of web into depth of flange divided by characteristic strength of pre-stressing steel. Okay, is equal to 0.45. FCK is given as 40. Okay, width of flange is given as 1200. Width of web just now we have calculated, that is 300 mm, into depth of flange is 150 and FP is given as 1600. Okay, calculate the answer. This is the answer. It is 1518.75 mm square. Okay. Now, if you get APF, then you can easily find APW, that is area pre-stressing steel required for web portion. Okay, we know that. Total area pre-stressing steel is equal to area pre-stressing steel required for flange portion plus area pre-stressing steel required for web portion. Therefore, APF is equal to AP minus, sorry, APW is equal to AP minus APF. Total area of pre-stressing steel is given as 4000 mm square minus APF is 1518.75. By this we'll get APW. Okay, APW how much will get? Check the answer. It is 2481.25 mm square. Okay, now you got APF and the APW. Okay, now we have to check whether the depth of neutral, whether our assumption is correct or wrong. Okay, to check assumption is correct or wrong, we have to find depth of neutral axis. For that, we have to use the code book. Okay, and in the problem, he says that post tension bridge girder with unbonded tendons. Okay, it is a post tensioned beam. Post tensioned beam means it will come under table number 12. Having unbonded tendons. Okay, if that tendons are unbonded, then it will fall under table number 12. If it is bonded tendon, it will fall under table number 11. Now we have to refer table 12, as it is said it is unbonded tendon in this problem. Okay, so referring to this table 12, first we have to find this ratio. Okay, we have to find this ratio. So here we have assumed that depth of neutral axis lies within the web. So this formula should be rewritten as APW into FPE divided by BWDFCK. Okay. Therefore, the ratio, I will copy the same formula AP divided by BDFCK. APFP divided by BDFCK. Okay. Is equal to, so we have assumed that neutral axis lies within the web. Then this formula should be rewritten as APW into FPE. Okay. Here the stresses after all the losses is given. That is why you need to consider FPE. If it is not given, then directly consider FP. FPE divided by BW into T into FCK. Okay. APW is just now we have calculated how much it is 2481.25. 2481.25 into FPE is 1000. Pre-stress after all the losses divided by BW 300 into effective depth 1600 FCK 40. Okay, if you calculate the ratio, you will get the ratio. Okay, 0.129. Okay, now with respect to this ratio, okay, that is for 0.129 ratio, we have to find the XU by D value. We have to find XU by D value. To find XU by D value, we need one more data, that is effective span to effective depth ratio. Here, okay, in the row, we have L by D ratio. Okay, here we have this ratio AP by BDFCK. So corresponding to these two ratios, we have to find XU by D value. Now you find effective span to effective depth ratio. Okay, effective span to effective depth. Effective depth is equal to L by D is equal to length of the beam is given as how much? Length of the beam, it is 24,000 millimeter and effective depth is 1,600 mm. So 24,000 divided by 1,600. If you calculate, you will get the ratio as 15. You will get the ratio as 15. Okay. Now corresponding to AP FP by BD FCK is equal to 0.129 and L by D is equal to 15. We have to find XU by D value. Okay, if you get to know about XU by D value, then you can find the XU, that is depth of neutral axis, and you can cross check whether your assumption is wrong or right. Okay. Now AP by BDFCK is 0.129. 0.129 means it will come in between 0.1 and 0.15, and XU by D ratio is 15, and it will fall between 20 and 10. 20 and 10. So here you need to do multiple okay, here you need to do multiple interpolation. Okay, multiple interpolation as we did for the previous classes. Write that table. Write the table so that it will be easy for you to do the interpolation. Here you write in the row, write APW FPE divided by BW DFCK. Okay. Then here L by D value. Okay, we know the value for 10, 10 and 20. We need to interpolate for 15. Okay, similarly with respect to AP FP by BD FCK, we have the value for 0.1 and 0.15. Here let me write 0.10 and 0.15. Okay, we need it for how much value? 0.129. 0.129. Okay. Now enter all corresponding values now. Enter all corresponding values. Now here refer to this table for 0.1. Okay, for 0.1 ratio, for 0.1 ratio, when L by D is equal to 10, the value is 0.36. When L by D is equal to 20, value is 0.32. I'll write those values now. When 0.1 AP, this ratio is 0.1, when and L by D is equal to 10, value is how much? 0.36, and for 20, 0.32. So here 0.36 and 0.32. Similarly, for 0.15, you write the values when L by D is equal to, sorry, when AP by BDFCK value is 0.15. Okay, when L by D is equal to 10, the XC by D is 0.52. When 20, XC by D is 0.46. So here 0.52 and 0.46. Okay. Now we need to interpolate for 15 now. For 10 value is known, for 10, 20 value is known, when 0.1 is the AP by BDFCK. So if you interpolate between these two, okay, you will get average of this two numbers, that is 0.32 and 0.36. Because 15 is the average of 10 and 20, you can directly calculate the average and write the answer directly. Otherwise, you can do the manual interpolation. You will get the same answer. So here the value that you get is 0.34 after interpolation between 10 and 20. Okay, for 15. Similarly, here if you do the interpolation between 10 and 20, if you get the value for 15, you will get the answer as 0.49. 0.49. Now, XU by D corresponding to 0.1 and L by D is equal to 15. It is 0.34. XU by D when AP by BD 0 is equal to 0.15, the value is 0.49. Now you need to interpolate for this 0.129. Okay, you need to interpolate between these two numbers. For 0.1, 0.34 is the XU by D ratio. For 0.15, 0.49 is the XU by D ratio. You need to get the value for 0.129. After interpolation, you will get the answer as 0.429. This is the final answer. 0.429. This is the final XU by D value. Okay, let me write. Let me take that value here for further calculation. XU by D is equal to 0.429. Okay, effective depth is known. XU by 1600 is equal to 0.429. Therefore, XU is equal to, if you multiply, you will get the answer as 683.2 millimeter. Okay, which is greater than depth of flange. Our assumption is correct. Okay, in most of the cases for box sections, the neutral axis lies in the web only. Okay, so 150 is the thickness of the flange. So XU is 683, which is greater than 150, which means depth of neutral axis lies within the web only. Hence, the assumption is wrong, correct. Hence, the assumption is correct. Okay. Now we can find the one more ratio, which is that one more ratio, this FPU by FP ratio. Okay, with the similar kind of interpolation, we need to find the value of FPU by FP. Let me read the table once again here. AP WFPE divided by BWDFCK. Okay. Here we have the value for same 0.10 and 0.15. We need to interpolate for 0.129. So here L by D ratio, we have the value for 10, we have the value for 20. We need to do the interpolation for 15. Okay, same table. Okay. Now enter the values. So for 0.10 corresponding FPU by FP for L by D is equal to 10 is 1.45 and 1.26. Let me enter the values here. 1.45 and 1.26. 0.26. Then here on the next value for corresponding to 0.15 AP by BW FCK, BD FCK, 1.36 and 1.20. 1.36 and 1.20. Okay, so interpolate between this 10 and 20 and get the value for 15. You will get the answer as 1.355 here. Here, if you interpolate between this 1.36 and 1.20, okay, and if you interpolate for 15, value 15, you will get the answer as 1.28. And further, if you interpolate between these two values corresponding to 0.129, you will get the answer, final answer as 1.355. 311. Okay. Now the FPU by FP value is equal to 1.311. Let me write the same thing here. FPU by FPE is equal to 1.311. Okay. Therefore, FPU divided by FPE is given 1000 is equal to 1.311. Therefore, FPU is equal to 1311 Newton per mm square. Okay. Now all the required parameters to calculate the moment of resistance are known. Just use this formula. Okay. Use this formula and get the value for moment of resistance. Let me copy this same formula here. Moment of resistance is equal to, we know that when depth of neutral axis lies within the web, moment of resistance is calculated as mu is equal to FPU into APW into D minus 0.42 XU plus FPE into APF into D minus DF divided by 2. Just substitute all the values, you will get the answer. Mu is equal to FPU, just before we have calculated, that is 1311 into APW, how much? APW 2481.25 2481.25 into effective depth 1600 minus 0.42 into XU. How much we got? XU 683.2 mm, 683.2 mm plus FPE is 1000 into APF is how much? APF is equal to 1518.75. 1518.75 into 1600 minus 150 by 2. Okay, therefore moment of resistance mu is equal to 6.58 into 10 power 9 Newton millimeter. Okay, or in terms of kilonewton meter, mu is equal to 6580 kilonewton meter. Okay, this completes the problem. If you get any doubts at any point of calculation, you can ask. Okay, thank you. Now, so the analysis problems are over. One more type of problems are there, that is design problem, design of a PSC beam, wherein you need to decide the sectional dimensions and you need to decide the area of pre-stressing as well, pre-stressing steel as well. Okay, for that there are some guidelines which we have to follow. Okay, next section of next section of this particular model is design of PSC beams. Okay, whether it may be rectangular or it may be T section or it may be I section. Okay, and we have to follow some guidelines for designing a PSC beam. Okay, design means here what? Deciding the cross-sectional dimensions and deciding the area of pre-stressing steel required is nothing but design. Okay, so we know formula for finding the moment of resistance. Okay, from IS 456. Here also for designing the PSC beam, what are the principle we have follow for design of RC sections? Same principle we will follow for design of PSC. That is why the formula from IS 456 is taken. Okay, moment of resistance. Okay, and I have copied the same formula which is there in page number 96 of IS 456. Here Usually for designing a rectangular section, we will assume depth of neutral axis as 50% of effective depth. Depth of neutral axis lying at the middle of the effective depth or 0.5 d. Okay. If you assume x is equal to 0.5 d, if you bring this d to the LHS, xu limit by d is equal to becomes 0.5. Okay. Therefore, if you substitute wherever xu limit by d is there, no, there if you substitute 0.5, here I have substituted in this step. Okay. And after further simplification, you will get the formula for mu, that is 0.14 FCK BD square. Okay, you need to remember this formula, students. Okay, for designing a rectangular section, mu is equal to 0.14 FCK BD square. Okay, then coming to the design of flanged sections, it may be the T section or it may be the I section. We have to decide depth of flange and width of web, correct? And there are some guidelines for choosing the depth of flange and width of web. Here we have a range for selecting height of flange. The height of flange is selected based on the effective depth. Okay, it is selected as HF by D is equal to 0.2 to 0.25, which is nothing but 20 to 25% of effective depth we have to select as depth of flange or HF, height of flange. Okay. 0.2 to 0.25 times D or 20 to 25% of effective depth we will assume as height of flange or depth of flange. Coming to the deciding width of web BW. Okay, this width of web is selected based on selected in between 20 to 30% of effective depth or 0.2 to 0.3 times D. Okay, so that ultimate moment mu varies from 0.08 FCK BD square to 0.12 FCK BD square. Okay, for rectangular sections, we will consider mu is equal to 0.14 FCK BD square. For I section or T section, we will consider from 0.08 to 0.12 FCK BD square. Generally, we will consider 0.10 FCK BD square. Okay, now we came to know how to select this thickness of flange. How much it is? 0.2 to 0.25 D. 2 to 0.25 D. And we also came to know how to select this width of web. How it is selected? BW is equal to 0.2 to 0.3 D or 20 to 30% of depth. Then coming to this width of flange for T section, it is assumed as 50% of the effective depth. Okay, 50% of the total height of the section or 50% of the total depth of the section. And for I section, 0.6 to 0.8 H we will select as width of flange. 60 to 80% of the total height of the member we will select as width of flange. Okay, these are all the guidelines we need to follow for selecting sectional dimensions of rectangular section or T section or the I section. Okay, I hope you got some idea on selection of this area of cross section or sectional dimensions. When we solve a real problem, then you will understand in a clear way. Okay, so with this, we'll solve one design problem now. All of you write this problem. All of you write this problem. Take 1 minute time. These are all very simple problems. Design problems are very easy. You can easily do it. Only the thing you need to remember the ratios, means how to select the sectional dimensions. Okay. Just go through the problem. A pre-tension pre-stressed concrete beam of rectangular section is required to support a design ultimate moment of 100 kN. Okay. The total moment acting on the beam is given. Design the section if FCK is equal to 50 Newton per mm square and FP characteristic strength of pre-stressing steel is 1600 Newton per mm square. Okay, let us see how to design the section. Solution. Now, see for rectangular section, what we have done, we have. Let me go to the theory part here. Yes. See, we have for rectangular section, what we assume is XU by D. We will take it as 0.5. Okay, let me take the same thing here. Assuming XU by D is equal to 0.5. Okay, if you assume XU by D is equal to 0.5, so MU becomes what? Go to the theory part. MU becomes 0.14 FCK PD square. Therefore, MU is equal to 0.14 FCK PD square. Okay. Now the question is how to select width of the section and depth of the section. Okay. Now assume V is equal to 0.5D. Okay. Assume for rectangular section, you assume B width is equal to 50% of effective depth 0.5D. Okay. Taking or assuming width of rectangular section as 0.5 times effective depth of the rectangular section. Okay. And MU is given in the problem only. How much it is given? 100 kilonewton meter. 100 kilonewton meter. It's nothing but 100 into 10 power 6 Newton millimeter. Then the FCK is given as 50 Newton per mm square. Just substitute everything in this formula. Now the formula becomes 100 into 10 power 6 is equal to 0.14 into 50 FCK. B is 0.5D. Okay. B we have assumed as 0.5D into D square into D square. Okay. Now this can be rewritten as D cube into this value. So you will get the D cube. So taking cube root, you will get the answer for effective depth. If you work out the answer, you will get the answer as 305.7 millimeter. Okay. Please cross check the answer. .7 mm. Okay. So we cannot practically give this odd number as effective depth. So we can assume we can round it up to 300 mm. Correct. Take D is equal to 300 mm. We can round it up to 300 mm. If we come to know about the effective depth, we can calculate the effective depth and B is equal to, we have assumed as 0.5 times D. Therefore, B is equal to 0.5 times 300. Therefore, B is equal to 150 mm. B is equal to 150 mm. Okay. Now you got effective width. Okay, or width of the section. You got the depth of the section as well. Correct. Now what next? We have to find area of pre-stressing steel. Okay. You need now cross-sectional dimensions are fixed. Width and depth of the member is fixed. What next? We need to design the reinforcement. We need to design the pre-stressing steel. Okay. Let us see how to decide the area of pre-stressing steel required. Okay. Again, we have to use this IS 1343 table for deciding this area of pre-stressing steel. Okay. Now in this design problem, what we assumed? We assumed XU by D is equal to 0.5. Okay. We assume XU by D is equal to 0.5. Now what we have to do is using 11. Okay. Using this table, it is a pre-tensioned beam. Correct. For pre-tensioned beam, of course, the table 11 we have to refer. Okay. Now we have assumed XU by D is equal to how much? 0.5. Corresponding to XU by D is equal to 0.5. Okay. 0.5 here. 0.5 means it will fall between 0.435 and 0.542. We need to find the corresponding FPU by 0.87 FP. Okay, I hope you are understanding. We have assumed XU by D is equal to 0.5. Okay, corresponding to XU by D is equal to 0.5, we have to find suitable APU by 0.87 AP value here. Okay, here you can see 0.5 means it will fall between 0.435 and 0.542. Corresponding to 0.435, APU by 0.87 AP is equal to 1.0. Corresponding to 0.542, corresponding value is APU by 0.87. AP value is 1. Therefore, for 0.5 also you will get the same 1.0 only. Okay. Now, from table 11 of IS 1343, from table 11 of IS 1343 1980, for XU by D is equal to 0.5, corresponding FPU divided by 0.87 FP is equal to 1. Okay. Therefore, this FPU becomes 0.87 FP. Let it be as it is. FP is equal to 0.87 FP. Okay. Now we know the formula for finding the moment of resistance here. For rectangle section, M is equal to APU AP into D minus 0.40 XU. Let me copy this formula here. We know that MU is equal to FPU into AP into D minus 0.42 XU. Therefore, here moment acting is how much? Moment acting given is 100 into 10 power 6. Substitute here 100 into 10 power 6 is equal to FPU is 0.87 FP, 0.87 FP into AP into D minus 0.42 XU. Okay. Now 100 into 10 power 6 is equal to 0.87 into FP is given, that is 1600. AP is unknown, keep as it is, into D is known. How much is the D? We have fixed 300 mm and B is 150 mm. 300 minus 0.42 into XU. XU is how much? Depth of neutral axis, how much we have selected? Depth of neutral axis, XU by D, we have selected at 0.5. Let me calculate here. See here, XU by D, we assume as 0.5. XU by D is 300 is equal to 0.5, which gives XU is equal to 150 mm. Okay, therefore here the answer is 150. Okay, XU by T we have assumed at 0.5. Therefore, XU depth of interrelaxation is equal to half of the depth of the beam. Okay, by this we can work out the area of pre-stressing steel. If you calculate the answer, you will get the answer as 303 mm square. Okay, so this completes the design. Therefore, finally you write a sentence: adopt a section of 150 mm by what is the effective depth we have chosen? Effective depth we have chosen as 300 mm. So there should be some effective cover. If you assume effective cover as 50 mm, so 300 plus 50, you will get 350 mm as overall depth. So let me write here as 350 mm with 300 mm square. You can round it off to area pre-stressing steel. You can round it off to 300 mm square of high tensile steel with high tensile steel with an effective depth of with the effective depth D is equal to 300 mm. Okay, so you need to highlight this sentence. This is what the design. Okay, you need to write a small diagram as well. You need to show the sectional dimensions and area of pre-stressing steel. So there is no detailed reinforcement for this design of PSC section, students. Just you need to show the sectional dimensions that you have decided. B is equal to 150 and effective depth overall depth is equal to 350 mm. Okay, here you can provide area of steel. So the effective depth is equal to 300 mm, and AP is equal to 300 mm square. Okay, so this completes the problem, design problem. Okay, got any if you need any clarification at any step of the design, you can ask students before moving on to the next design problem. Okay, thank you. Now we'll move on to the next design problem. Please note this problem, all of you. This is the problem on I section. You have to design an I section here. Go through it. A post-tension bonded beam. He says that it is a bonded beam of unsymmetrical I section is required to support a design ultimate moment of 1200 kN. Determine the overall depth and thickness of the compression flange required if FCK is equal to 35 Newton per mm. P is equal to 1500 Newton per mm square. We have to find overall depth, okay, and thickness of the compression flange. Compression flange means the top flange. Okay, it is a unsymmetric I beam. In that we have to find the dimensions of the top flange. Okay, write the given data first. Write the given data solution. Here, moment acting on the beam is given as 1200 kilonewton meter. In terms of Newton millimeter, it is 1200 into 10 power 6 Newton millimeter. Okay. Then FCK is given 35 Newton per mm square. FP is given as 1500 Newton per mm square. Okay. So for I section, you go through the guidelines for I section. Yes, here we have all the guidelines. We have to follow these guidelines. Okay. Now, first you fix the uh, width of flange. Here the guidelines says that to fix for I section to fix the width of flange as 0.6 to 0.8 times the depth. Okay. We have now we have to use these guidelines for fixing the dimensions. Okay. Here for I section, even you can assume the width of web or width of flange up to 0.5 times the depth as well. Okay. Even you can go for 0.5 times effective depth also. Okay. Here the range is given as 0.6 to 0.8. Even you can go for selecting width of flange as 0.5 times depth as well. Okay. Now for this problem I have solved using by assuming this width of flange as 0.5 times d, and I got all the checks satisfied. Okay. All the checks have been passed. Now what I will do, I will assume width of flange. Okay. Assume width of flange as 0.5 times effective depth. Okay. And width of web. Okay. Width of web. Here the guideline says that it should be selected between 0.2 to 0.3 times effective depth. VW should be 0.2 to 0.3 D. We will select the middle value 0.25 will select. Okay. 0.25 D. We will assume VW as 0.25 D. Okay. And one more guideline, assuming this MU between 0.08 FCQ BD square to 0.12 FCQ BD square, I will assume in between value that is 0.10 FCQ BD square, and taking MU is equal to 0.10 FCK BD square, 0.10 FCK BD square. Okay. Therefore, here 0.10 FCK B is nothing but 0.5 D, 0.5 D into D square. Okay. Finally, 0.1 into 0.5 will be 0.05 FCK D cube is equal to MU. Therefore, D cube is equal to MU divided by 0.05 FCK. MU is given. How much it is given? 1200 into 10 power 6. Substitute here. 1200 into 10 power 6 divided by 0.05. FCK is given as 35. Okay. FCK is given as 35. So by this we will get the effective depth of the section. We will get the effective depth of the section as 881.82 millimeter. 881.82 millimeter. Okay. So we have to round up this value. Okay, you can just round it up to d is equal to 1000 mm. Okay, d is equal to 1000 mm. Okay, I have rounded it. I have rounded it up to 1000 mm. Okay, and b is equal to width of flange. We assumed as 0.5 times effective depth. Therefore, 0.5 times 1000 means you will get the width of flange as 500 mm. You will get the width of flange as 500 mm. Now you have selected width of flange and depth of effective depth of the eye section. Few more things you need to decide, that is thickness of the flange you need to decide, and thickness of the web also, or width of web also you need to decide. Okay, thickness of flange, height of flange. Height of flange, he says that to select the range in between 0.2 to 0.25 HF by D. Okay, I'll take 0.2. Okay, HF by D. Assume thickness of top flange is equal to HF is equal to, so here range is from 0.2 to 0.25. I will take 0.2. HF is equal to 0.2D. I will take 0.2D is equal to 0.2 into 1000 is equal to 200 mm. Okay, why I selected 1000 mm means here why I rounded up to 1000 mm means you will get here full numbers. Okay, you will not get any rational numbers here. For that purpose, I have selected 1000 mm. 0.2 into 1000 is 200 mm is the height of flange. Then thickness of web. Thickness of web is equal to BW is equal to, the guideline says BW should be selected between 0.2 to 0.3 BW by D. I will go for selecting 0.25. Okay, 0.25 D. 0.25. Here you make a small correction. Here BW by B it is, not the D. Okay, BW by D. Okay, make a small correction here. Therefore, here BW by B means it becomes D becomes B here. Okay. So the width of web is selected based on width of the flange. 20 to 30% of the width of the flange. Okay. Therefore, here 0.2 is B, 0.25 into width of flange. How much we got? 500 mm here into 500. So the answer that you get is 125 mm. 125 mm. Okay. There's no problem even if you go for higher value. Okay. Okay. Now we have decided all sectional dimensions, correct? Width of flange, thickness of flange, width of web, and effective depth of the eye section. So the deciding of sectional dimensions is over. Next is to decide or to calculate the area pre-stressing still required, correct? For that, what is the procedure we have followed for the previous problem? Same procedure we have to follow here. Okay, so as this is the I section, we have to assume either case 1 or case 2. Okay, my suggestion is for designing an I section, you assume case 1 only. What is case 1? Depth of neutral axis lies within the flange. Okay, especially you assume it as depth of neutral axis is equal to depth of flange. Okay, here you write that sentence, assuming neutral axis depth neutral axis depth XU is equal to depth of flange only or height of flange only as 200 mm. Okay, which will fall under case 1 only. Neutral axis lies within flange. It will fall under case 1 only. Okay, if it is the case 1, then no need to use this formula, detailed formula. Okay, as we followed for the previous one of the previous problem in this class. Okay, you can just directly refer the table and the formula which is there in the code book. Okay, for that purpose, what I'm telling is assume depth of neutral axis lies within the flange only. You need to design, which means that you are designing the I section so that neutral axis lies within the flange only. That is the meaning. Okay, it is left to you. Okay, therefore XU by D. Okay, therefore XU by D is equal to XU, we assume it as 200 mm. Effective depth we got it as 1000 mm. This ratio becomes how much? This ratio becomes 0.2. Okay, then what next? Using this XU by D is equal to 0.2, you need to find corresponding FPU by FP value. Corresponding FPU by FP value. Just go through the problem whether it is post-tension beam or pre-tension beam. Let me go through it. It is a post-tension bonded beam. Post-tension bonded beam means table 11 only. Okay, post-tension bonded beam only. B means table 11 only. Here, you need to refer this column. Okay, now XU by D value is known. How much we got? XU by D is equal to 0.2. XU by D is equal to 0.2 means here with effective bond, post-tensioning with effective bond, XU by D is 0.2 means it will fall in between 0.109 and 0.217. And when XU by D is equal to 0.109, corresponding FPU by 0.87, FP is 1. Similarly, when XU by D is 0.217, corresponding FPU by 0.87, FP value is 1.0. Therefore, corresponding to 0.2, you will get the same one value only. Correct? So, therefore, from table 11, you write from table 11 for XU by D is equal to 0.2, corresponding FPU by 0.87, FP is equal to FPU by 0.87, FP is equal to 1.0. Okay, therefore FPU is equal to, therefore FPU is equal to 0.87 FP. FP is equal to 0.87 FP. Okay. Now utilize this formula, moment formula. You can get the area of pre-stressing steel now. M is equal to APU AP into D minus 0.42 XU. We know that. We know that M is equal to FPU into AP into D minus 0.42 XU. Okay. Page number 59. Therefore, moment is given, moment acting on the beam. It is given as 1200 into 10 power 6. 1200 into 10 power 6 is equal to FPU is 0.87 FP into AP into effective depth. We got it as 1000 mm. 1000 mm minus 0.42 into depth of neutral axis. How much we assumed? 200 mm into 200. Okay, into 200, and FP is given, no? FP, how much it is given? FP is 1500 Newton per mm square. I forgot to substitute here. Let me substitute the FP as 1500 into 1500. Okay. So only AP is the unknown parameter here. You can solve for AP and you can get the value for area pressure steel. If you work out the answer, you get the answer as 1003 mm square. Okay. 1003 mm square. We can round it up to 1000 mm square. Okay. Therefore, the design details. Therefore, the design details are effective depth. We got it as 1000 mm. Okay. It is asked to find the dimensions of the top flange only in the problem. Okay. Here, let me write the precision steel here. T is equal to 1000 mm and width of flange or B is equal to how much we got? B is equal to 500 mm. 500 mm and HF height of flange. How much we got? 200 mm. 200 mm. Then what else? Width of web. We got it as 125 mm. BW is equal to 125 mm. Then area of pressure steel AP. How much we got? 1000 mm square. 1000 mm square. These are all the given the design details. Okay. So to this the problem is completed. Any doubts you can ask. Thank you. We'll move on to the next problem. Problem number 3. Write the problem. This is somewhat different problem. Go through it. A pre-stressed road bridge of span 10 meter. Okay. A pre-stressed road bridge of span 10 meter consists of a concrete slab 380 mm thick with parallel post-tension cables in each of which the force at transfer is 360 kilonewton. Pre-stressing force is 360 kilonewton. If the bridge is required to support an uniformly distributed applied load of 25 kilonewton per meter square, and the lay load on the beam is given with tensile stress in the concrete not exceeding 0.7 Newton per mm square at any time. Calculate the maximum horizontal spacing of the cables, comma, their distance from the soffit of the midspan. Okay, from soffit of the slab at midspan and their lowest possible position at supports. Assume 20% loss of pre-stress after the transfer. Okay. Now it is a pre-stressed concrete slab. Okay. For this, what is asked is the horizontal spacing of the cables we have to find, and the cable profile at midspan. What should be the distance of the cable from the soffit? At the support also, what should be the distance at the distance from the soffit of the beam? Distance of the cable from soffit of the beam, that we have to find. Okay. Now, in general design of slab, what we'll do, usually we'll design the slab for 1 meter length. Okay, we'll design the slab for 1 meter length, and same thing we'll apply, same design we'll implement for the next each and every meter of the slab. Okay. Now, initially we'll take 1 meter width of the slab. Okay, for design purpose. Okay. Solution. Considering 1 meter width of slab, that is 1000 mm width. Okay. Always while designing the slab, what is the general procedure we follow? We will design the slab for 1 meter width, and same thing we will apply it for the next spans. Okay, next portion of the slab. Okay. Therefore, as we have considered 1 meter width of the slab, means P is equal to 1000 mm we have considered. Okay. And he says that the slab is 380 mm thick. Let me take 380 mm depth. 380 mm. Okay. 380 mm. Therefore, the area of cross section will be how much? Area of cross section of the slab. Therefore, area of cross section A is equal to 1000 into 380. Okay, you will get it as 38 into 10 power 4. 10 power 4 mm square. Sorry, mm square. 38 into 10 power 4 mm square. Okay. We have decided the cross section of the slab, that is 1000 mm by 380 mm, and cross sectional area also we determine, and also find some basic sectional properties like section modulus. Section modulus, this is required for further calculation. I'll tell you where it is required. Sectional modulus or sectional modulus. Section modulus is equal to I by Y, where I is equal to BDQ by 12, B is 1000 into D is 380 Q by 12 is equal to, you'll get the answer as 4.572 into 10 power 5 mm4. Okay. Then Y is equal to what? For rectangular section, it is depth divided by 2. Depth is 380 divided by 2. We'll get the answer as 190 mm. Therefore, Z is equal to I is 4.572 into 10 power 5 divided by 190. Or else directly you can use BD square by 6 formula. You'll get the same answer. Z is equal to BD square by 6 formula. By this, you get the section modulus as 24.06 into 10 power 6 mm cube. Okay. Now, here he has given one condition. Is given one condition. That condition is a pre-stressed road bridge of span 10 meters consists of concrete slab, 380 mm thick parallel post tension cables, in each of which force of transfer is 360 kN. If the bridge is required to support an uniformly distributed applied load of 25 kN per meter square, with the tensile stress in the concrete not exceeding, this is what the condition, with the tensile stress in the concrete not exceeding 0.7 Newton per mm square at any time. This is very important. At any time. Okay. There are two time constants for any PSC bridge, that is at transfer and at service load. Okay. The condition given here is the maximum tensile stress in concrete is 0.7 Newton per mm square at any time, whether it may be at transfer condition or it may be at service condition. Now we will utilize this condition. Okay, and we will utilize this condition and we will find the total pre-stressing force in the member. Okay, we will find total pre-stressing force in the member. Okay, see, he says that post tension cables in each of which the force at transfer is 360 kilonewton. Okay, but number of cables is not given. If number of cables are given, you would have determined the directly the total pre-stressing force. It is not given. Okay, he says that there are few number of cables. Each cable is carrying 360 kilonewton. If cables are directly given, you would have calculated directly the pre-stressing force by multiplying the area and the by multiplying the number of cables into force in each cable. But that is not given. Okay, for that, for finding the exact pre-stressing force, total pre-stressing force that exists in the member, he has given a condition, that is total, the maximum tensile stress will not exceed 0.7 Newton per mm square. Okay. Now at any time means we will take two time constants. Okay. Here I'll rewrite that condition. Limiting tensile stress in concrete at any time is equal to 0.7 Newton per mm square. Okay. At any time means we will take two time constants, one at transfer. One at transfer will take at transfer there will not be any live load, only pre-stressing force and moment due to dead load will be there. Okay, F superior is equal to P by A minus PE by Z plus mg by Z is equal to maximum tensile stress. He says that maximum tensile stress is represented by negative sign minus 0.7 Newton per mm square. Call this as equation number 1. Okay. At transfer, there will be only effect of pre-stressing force and moment due to dead load. Okay. P by A minus PE by Z plus mg by Z is equal to 0.7 Newton per mm square. Okay. Already you are familiar with this condition, students, in the first module. I am not going to explain it in detail about these equations. Okay. If you want any clarification, you can just refer to the lecture videos of module 1, or you can refer to the notes of module 1. Okay. So this is what the equation we get at transfer. Okay. F superior equal to P by A minus PE by Z plus mg by Z. Okay. At service condition, we will write F inferior is equal to P by A plus PE by Z minus mg by Z minus mq by Z is equal to minus 0.7 Newton per mm square. Call this as equation number 2. Okay. Now you may get doubt that at transfer condition you have written the formula for F superior. Okay, for tensile stress. At service conditions we have written the formula of F inferior. What may be the reason? The reason is that at a transfer condition, there will not be any live load. Okay, there will not be any live load. There will be hogging moment. Okay, therefore, the maximum tensile stress will take place at the top fiber at transfer condition. Okay, at transfer conditions, there will be only pre-stressing force. There will be only pre-stressing force and there will be some dead load of the beam. Due to this pre-stressing force, there will be hugging moment of the beam, which causes top fiber the top fiber for which the tensile stress. Therefore, I written the F superior formula. Okay, so at transfer condition, maximum tensile stress takes place at the top fiber, that is the F superior formula. Similarly, at service condition, there will be live load along with the dead load of the beam. In that case, the beam undergoes sagging bending moment. When it undergoes sagging bending moment, the bottom fiber will undergo tensile stresses. That is why you should write the formula of F inferior. This you remember. Don't get confusion. Okay, don't get confused. At transfer condition, the maximum tensile stress takes place at the top fiber. At service condition, the tensile stress takes place at the bottom fiber. This much you remember. You need to write the corresponding formula. Okay. For further detailed information, you refer module 1. Okay. So this is what the two conditions. Okay. And one more thing. In the problem, he says that assume 20% loss of pre-stress after transfer. So here second formula is the formula which is after the transfer, during service, nothing but during service. So for this we have to apply 20% loss of pre-stress. Okay, considering 20% loss of pre-stress. Considering 20% loss of pre-stress, the formula can be rewritten as F inferior is equal to, if you assume 20% loss, then it becomes 80%, nothing but 0.8 P divided by A plus 0.8 PE by Z minus mg by Z minus mq by Z is equal to minus 0.7. Call this as equation number 3. Okay. Now we have to find all the required values now. Okay. Pre-stressing force is the unknown parameter here. That only we have to find. Okay. Sectional area is known. Area of cross section of the slab. We have determined at the initial stage only 38 into 10 power 4 mm square. 38 into 10 power 4 mm square. Then what else is required? Eccentricity is also not known. Okay, you keep as it is, no problem. Eccentricity is also not given, or else it is not known. But sectional modulus we have calculated. How much is the sectional modulus? 24.06 into 10 power 6. 24.06 into 10 power 6 mm cube is the section modulus. Then what else is required? Mg and Mq are required. Correct? Mg and Mq are required. Mg is nothing but dead load moment. Correct? Mg is nothing but dead load moment. First you find self weight of the beam or self weight of the slab. Self weight of slab is equal to cross sectional area into density. Okay, cross sectional area is 38 into 10 power 4 mm square. You need to substitute here in terms of meter square. Correct? In terms of meter square, it is 10 power minus 3 whole square. Into densities, the density of precious concrete is 24 kilonewton per meter cube. By this, you'll get the dead load of the slab or dead weight of the slab or self weight of the slab. That you get it as 9.12 kilonewton per meter. 9.12 kilonewton per meter. Okay, you can find dead load moment now. WL square by WGL square by 8. Okay, therefore 9.12 into total length of the slab is given 10 meter. Correct? Into 10 square by 8 into 10 square by 8. Okay, by this you'll get mg as 114 kilonewton meter. Please cross check the answer. So you'll get the dead load moment. Okay. Then live load moment. You can calculate now. MQ is equal to. Okay. MQ is equal to same formula WQ L square by 8. Okay. Live load on the slab is given. How much it is given? 25 kilonewton per meter square. Okay. 25 kilonewton per meter square. So per meter area, the lay load given is 25 kilonewton per meter square. We are designing for 1 meter length of the span. Correct? 1 meter length of the slab. Therefore, WQ is equal to 25 into WQ live load on the slab given is how much? 25 kilonewton per meter square. Okay, WQ. So we are designing for 1 meter width of the slab. Therefore, WQ is equal to 25 into 1 meter. So it becomes 25 kilonewton per meter. Okay, 25 kilonewton per meter. Therefore, the live load intensity is 25 into length 10 square by 8. By this, you'll get live load moment MQ is equal to 312.5 kilonewton meter. 312.5 kilonewton meter. Okay. Therefore, now we got mg, mq, we got section modulus, area of cross section is known. Just substitute everything in equation 1 and equation 2. Sorry, equation 3. Okay. First, you substitute in this equation 1. Equation 1 becomes, therefore, equation 1 becomes substitute everything f superior p by a first, p by a, p by area is 38 into 10 power 4, then minus pe by z, minus pe by z is how much? 24.06 into 10 power 6. 24.06 into 10 power 6 plus mg by z plus mg by mg is how much? 114 kilonewton meter, nothing but 114 into 10 power 6 Newton millimeter divided by same Z 24.06 into 10 power 6 is equal to minus 0.7. Okay. So if you can rewrite this equation, 1 by 38 into 10 power 4 will give 2.631 into 10 power minus 6 P minus 1 by 24.06 into 10 power 6 value will be 4.156 into 10 power minus 8 PE plus value of this constant is 5.438 is equal to minus 0.7. Call this as equation number 4. Okay. Similarly, substitute the values in equation number 3. Okay. F inferior 0.8 P by A 0.8 P by A is 38 into 10 power 4. Then what else? Plus 0.8 P by Z plus 0.8 P by Z is 24.06 into 10 power 6. Then mg by Z is there minus 114 into 10 power 6 divided by 24.06 into 10 power 6 minus mq by Z. mq by Z is there. mq by Z 312.5. What is the value of mq? 312.5 into 10 power 6 divided by 24.06 into 10 power 6 is equal to minus 0.7. Okay. Simplify this equation. 0.8 divided by 38 into 10 power 4 will give 2.105 into 10 power minus 6p plus 0.8 divided by 24.06 into 10 power 6 will give 3.325 into 10 power minus 8 p minus, and value of this term, these two terms will be 17.02 is equal to minus is equal to 0. If you take this minus 0.7 to the LHS, okay, and simplify, if you will get 17.02 is equal to 0. Here also make a correction, it is 0 only here also. If you bring this minus 0.7 to the LHS and simplify, you'll get 5.438. Okay, call this as equation number 5. Equation number 5. Okay. Now you can refer to equation number 4 and 5. These are two linear equations with two unknowns. One unknown is P and one more unknown is PE. Okay, you can solve these two linear equations in your calculator only. After solving, you'll get the value of P and PE. Okay, solving equations 4 and 5. Solving equations 4 and 5, you will get the value of P. P is equal to, you will get it as 3009 into 10 power 3 Newton. And you will get the value of PE as 3.213 into 10 power 8. 10 power 8. Okay, now you can substitute the value of P here. 3009 into 10 power 3 into E is equal to 3.213 into 10 power 8. By this, we will get the eccentricity. We will get the eccentricity as 106.7 millimeter. 106.7 millimeter eccentricity. Okay. What is eccentricity? Let me read the diagram. Okay, so this is what the eccentricity we got. E is equal to how much we got? 106.7 millimeter. Okay, overall depth of the beam is 380 mm. Overall depth of the beam is 380 mm. Okay, so depth of neutral axis will be 190 mm. 190 mm. Okay, 190 mm. Okay, you just look into the question. What is the question here? Calculate the maximum horizontal spacing of the cables, that is one aspect, and the distance from the soffit of the slab at midspan. Okay, we need this value, distance of cable from soffit of the span. This distance we need. Okay, so the eccentricity. So this distance will be how much? Soffit of the span. Therefore, distance of cable from soffit at center is equal to 190 minus 106.7. Okay, overall 190 minus 106.7 if you do, you'll get distance of cable from soffit of the span as 83.5 mm. Okay, I hope this is clear for everyone. Then one more question. And their lowest possible position at the supports. And their lowest possible position at the supports. Here you write to find lowest possible position of cable at support. Lowest possible position of cable at support. Now, in this case, you need to substitute the moments corresponding to supports only. Okay. When you calculate moment at support, moment due to dead load and live load at support, it will be 0, correct? At support, mg and mq will be 0. Mg and mq will be 0. Okay. Therefore, the equation 1 becomes, therefore, equation 1 becomes, refer to the equation 1, P by A, P we got the value 3009.9 into 10 power 3. 10 power 3 divided by area of cross section 38 into 10 power 4 minus P by Z. P is 3009 into 10 power 3 into, we are interested to find lowest position of cable at support. Okay, here eccentricity will vary. Eccentricity will vary at the support here. Okay, I'll keep as it is, eccentricity divided by Z. Z is how much? 24.06 into 10 power 6. 24.06 into 10 power 6 is equal to minus 0.7. By this, we'll get the eccentricity as 68.91 millimeter. Eccentricity at the support. This is eccentricity at the support. Let me write the diagram again. This is the centroidal axis. This is the cable profile. Eccentricity at the support, we got it as how much? 68.91 millimeter. 68.91 millimeter is the eccentricity at the support. Okay, and it is asked to find lowest possible position of cable at support from soffit of the beam. What will be the distance? That is the question. Total is 150. How much it is? Total is 190 from soffit. Distance of center from the soffit is 190. 190 minus 68.91 will give distance of cable from soffit at the support. Therefore, distance of cable from soffit is equal to 190 minus 68.91. Okay, we'll get the answer as 121 millimeter. Okay, this completes the problem. If if you have any doubts at any point of calculation, you can ask students. So this is a quite different problem, but it is easy only. Okay, you need to remember these two conditions. Rest all the simple calculations only. You can get the answers. I hope this is clear for everyone. Thank you, students. With this, I will stop the class and we will continue in the next class. Thank you.